Hi, I'm Dr. Jim Zoval, a professor of chemistry at Saddleback College. You're about to watch one of my video lectures. If you like this lecture, you can get the entire Allied Health General Organic and Biochemistry course from the website address you see on the screen right now. Be sure to type the underscore between VOD and pages in this address. Enjoy the video. We need to know about polar bonds. So I just told you a way to know if a bond is polar or not. In this class, if they're the same atom, like H and H, nonpolar. If they're different atoms, polar, unequal sharing. Make sense? Okay? So let's think about now the polarity of the molecule. We talked about bond polarity. Let's think about the polarity of the molecule. In the case of simple diatomic molecules like this, there's only one bond, and it's either polar or not. So if you have homonuclear, same atom, this bond isn't polarized, so the molecule is nonpolar. If you have two different atoms, heteronuclear, unequal sharing, there's just one bond, polar molecule. So see, for diatomics, it's real easy. Just look at the bond. Is it polar or not? Same thing is true for the molecule. Well, that was pretty easy for diatomics to know if the molecule is polar. You see if that one and only bond is polarized. How do we know, Cartman says, how do we know if a larger molecule is polar, a molecule with more than one bond in it? We're going to break these, to know if a molecule is polar, we're going to break them up into classes. The first class we just looked at is diatomic. All right? And we'll just review if it's homonuclear, same atom, then it's nonpolar, right? If it's heteronuclear, then it's polar. The next class of molecules we're going to look at are called small molecules. I guess if these are small, these diatomic are really small. So it's really small molecules. Let's define our small molecules as, definition would be there's one central atom, just one central atom, and all other atoms are bonded to the central atom. So how do we know if small molecules are polar or not? What we're going to do here, and we're going to do this by demonstration, is we're going to add up all the dipoles. I want to show you this by example. So let's consider the CO2 molecule. Remember we did the shape and the line bond structure for CO2. There's no lone pairs, so it had this linear shape right here. Notice there are two polar bonds in the CO2 molecule. How do I know there's two polar bonds? How do I know that's a polar bond? Right, this one right here. Yeah, two different atoms, so they don't share the electrons evenly. So I know that I have, and same thing here, right? So there's two polar bonds there. This results in two dipoles. Remember, doing this and doing this is the same thing. The arrow points to the negative side. Now, you notice how symmetric those arrows are? See how they're pointing exactly opposite one another? One goes this way and one goes this way, right? That molecule's symmetric. Since the molecule's symmetric, those dipoles cancel each other out and the molecule is nonpolar. I want to show you that with something you're more familiar with. Remember how I told you that these arrows, we treat different things with vectors, and force is one of them. Force, not only can I push on something or pull on something, but I could pull, say, in this direction or in this direction. So it has a magnitude, how hard I pull and the direction I pull. Okay? Would you come up and we'll demonstrate this. let's get right here. And you take your right hand, go like this. Now pull just a little bit. Don't pull me over, I might fall on you. Okay, a little bit. So you're pulling a little bit straight back towards that wall, right? And I'm pulling a little bit too. So she's exerting a force, and I'm exerting a force in exactly the opposite direction. And our hands moving? No. So what's the net force exerted? 0, right? We're adding these force vectors up, and we're getting a net of 0. If I pulled a little bit harder, we'd go this way. If she pulled a little bit harder, we'd go, when we pull the same and in exactly opposite directions, adds up to 0, right? Thank you. Same thing happens with electric dipoles. They cancel each other out. Since the molecule is symmetric, the dipoles cancel each other out, and the molecule is nonpolar. Notice, we started with a molecule with 2 polar bonds, but we end up with a molecule that's nonpolar. So just because you have polar bonds in a molecule doesn't necessarily mean you have a polar molecule. I want to show you another example. Let's look at water as an example. So there's our water. Remember the water molecule, right? It has 4 electron groups, right? 2 lone pairs and 2 bonded atoms. So you have these 110-degree bond angles. 2 polar bonds. That's a polar bond. Hydrogen, oxygen are different. Hydrogen, oxygen are different. Results in 2 dipoles. Oxygen's more electronegative than hydrogen, so the oxygen gets a partial negative. Hydrogen gets a partial positive. We could do this with the arrows, or we could do this with the del minus and del plus. You notice that these aren't exactly symmetric, right? They're not going right towards each other. Right? Since that water molecule is not symmetric, the dipoles do not cancel each other out. And the overall molecule has a positive and negative side. The molecule now has one side that's more negative and the other side that's more positive. That's a polar molecule.
But wouldn't it be the lone pairs then that create the polarity?
Well, you're onto something there, and we're going to get there in a moment. Yes, very good insight. Could I get you to come back up? And I want to demonstrate this is why these don't cancel out when they're not exactly opposite one another. So instead of pulling straight towards the wall, we're going to hold our arms like those dipoles, but you're going to pull kind of down to that corner, and I'm going to pull. Do you see how these are adding up to not this or this? They're adding up. They're not going to 0, but we're going down like that. So they don't cancel each other out. Just like the forces don't cancel each other out, the polarized charge doesn't cancel it out. So when the molecule is not symmetric, those dipoles do not cancel each other out, and the molecule is polar. And someone said something with very good insight. What do you think throws the symmetry off? The lone pairs, right. I want to show you a couple other ways to think about this dipoles not canceling out. One way was what we just demonstrated with forces. Another way is how mathematicians add up these dipoles. There's a geometric way to do them. To get the resultant dipole, when you add 2 dipoles, you either get 0 when they cancel or some other dipole when they don't cancel. Here's how you do it. You put the dipoles, you don't change the angle or the length, but you put the arrows head to tail, and the resultant, that dipole plus this dipole adds up to that. So wherever they start and wherever they end, put them head to tail. So that means this water now has this dipole where this side of the water molecule is partially negative. Remember the arrow and the negative? And this side of the water molecule is partially positive. One of the reasons water is unique is because these are quite strong dipoles. There's a big difference in electronegativity between oxygen and hydrogen. So when you start with 2 large dipole, you get a quite strong dipole. So water is a very polar molecule. That's one reason it's unique. We'll see another reason it's unique shortly. Let's think about what would happen if we did that with the CO2. Here's the CO2. CO2 is linear, right? So you have one dipole that goes like this, and you have another one that goes like this. Yeah? Same magnitude. The arrow is the same length if I draw them right. Now we're going to put them head to tail. So here's this first one here, and I'll put this one tail on the head of that. Notice it goes right back to where I started. And so unlike the previous example, it adds up to 0. There's one other way you could think of this. I like to give you guys as many ways to think about it as I can, because these are kind of abstract things. If we look at the water molecule, it's shaped like this. And remember, the oxygen's partially negative and these hydrogens are partially positive. Here. So there's only one atom in here that gets the partial negative. So the partial negative resides right here. Now if we think about partial positive, there's a positive center here and partially positive center here. You see that the center of positive charge would be if I drew a line between these and put a point right in the middle. This is where the center of positive is. Positive here and positive here. The geometric mean is right there. Notice they're not on the same spot, so you get an overall dipole. If we did this with CO2, oxygen's partially negative, the carbon is partially positive, so the center of positive charge is right here. You see how the center of negative charge is in the exact same spot? That's another way to see those dipoles cancel out. Hi, I'm Dr. Jim Zoval. If you like this video and you'd like to get the entire course or just some of the chapters on video, I have the entire course in video lectures at the website you see on the screen right now. They're available on demand. The period of the rental is for a full year, so you'll have this video through the entire course. You could watch it as many times as you want, whenever you want. Happy studies.